So our first example for chi-square goodness of fit test is going to feel real familiar to the activity we did in class. You were testing a die. It's kind of a common application of the chi-square goodness of fit test, easy way to describe the goodness of fit test to someone. Here we have Jenny has a six-sided die. She rolls it 60 times. So calculate the expected counts. Well, if it's a fair six-sided die, and we'd expect each outcome to be equally likely, we'd expect our expected counts to all be 10 each. Okay. Now the chi-square, you're going to see chapter 11 only has 2 sections to it. The second section has 2 different chi-square tests, but they both feel really, really the same. And they can be a little bit hard to differentiate between, and maybe you will misname them sometimes. But the goodness of fit test is always going to be really easy to identify because it's only ever going to give you one list. Now, you need 2 lists to execute it, right? We're going to definitely need 2 lists to execute the goodness of fit test, but generally your data is going to be collected in one list, and we're trying to see, does this list of numbers, this distribution of numbers, follow a particularly claimed distribution of numbers, okay? So our chi-squared test statistic, we saw this on our formula sheet previously. It's a pretty simple formula, but we don't have to memorize it because it's right here on our formula sheet. We have our observed counts minus the expected. We square that quantity and divide by the expected. So we kind of get these fractions or ratios, and we're going to add them up. That sigma notation there for sure means to sum up. So the way that we would calculate that here, if we think about our observed minus our expected squared, and it's a summation here, divided by the expected each time. Right? So my first observed count was 13 minus 10. We'll square that, and we would divide by the 10. We're going to keep adding those up. But as we saw previously, the calculator actually will do this for me. I'm going to go to Stat and Edit on my calculator and enter those 2 lists. And we can observe our biggest deviation from what we'd expect would be that 6, difference between the 6 and the 10. But we want to see if overall there's a significant deviation from what we'd expect. So we go to Stat and Test, and I arrow up. I think I can find my chi-squared test quickly. And you can see there's 2 other tests, but we only have 1 chi-squared test on our calculator because the other 2 are executed the exact same way. We just articulate the names of them a little bit differently. So we have L1 is our observed list, L2 is our expected, and our degrees freedom is still 5. We have 6 faces of the die, 6 categories that our variable can be distributed among, so that means we have 5 degrees of freedom. So we get a chi-squared statistic of 3.4. So even without typing all that in, I can see my chi-squared statistic is 3.4, and here if we cheat ahead a little bit, we know that we did that right. Using the appropriate degrees of freedom, calculate the p-value. So again, if I jump over to my chi-squared formula sheet, so I'm going to be looking at 5 degrees of freedom, and I'll point this out here. Here's my chi-squared lever, and if I'm looking for 3.4 for 5 degrees freedom, and notice we ran into this issue before, 6.3 is as low as it goes, so 3.4. So we know the p-value has to be bigger than 0.25, right? This is the area in a right tail. So if 6.63 lives here, and the area to the right of that is 25%, well, surely the area to the right of 3.4 is going to be much bigger than 25%. And then we can look on our calculator and see the p-value is 0.6385, or if we just round that to 2 decimal places, we get a p-value of about 0.64. And not a big surprise, maybe you've seen this on your calculator, but if we hit second and the vars key, maybe this jumped out to you, but you can see there's a chi-squared CDF, just like normal CDF, just like TCDF. So if our lower limit is 3.4, remember this is always a right-tailed situation, so we'll just put a really big number out there to the right, and our degrees freedom is 5, we should get a p-value of 0.64. And it finds that area under the normal curve like we've been doing for a pretty long time now. Okay, and what conclusion can we make about her die? with the p-value 0.64, it seems like a chi-squared statistic of 3.4 is not unusual to occur for a fair die. So if we were to make a formal test here, our null hypothesis would be that the die is fair. There's nothing abnormal about it. Our alternate would be that the die is not fair. It rolls differently than a fair die. But since the p-value is 0.64, way bigger than any alpha value, we don't have any significant evidence that her die is not fair. And of course, keep in mind our condition for inference, we still want to have a simple random sample. Rolling a die is pretty obvious way to go about doing that. And we want our expected counts to all be at least 5. In this case, they were all at least 10. Okay, so here we have a chi-squared hypothesis test we'll be able to do start to finish, right? As soon as I see, do these data provide convincing evidence, I know I'm going to do a hypothesis test. We could use the template. I'm not going to use my template. I'll kind of just use it in my head. I'll go through all the steps that would be found in it. But it says, according to the U.S. Census, of all U.S. residents age 20 and older, 19.1% are in their 20s, 21.5% are in their 30s, and so on down. So what we went out and what they've gone out and looked at is here. They have a table that shows the age distribution for a sample of U.S. residents aged 20 and older. Members of the sample were chosen at random by dialing landline telephone numbers. So the question that we have is, does the distribution of these people that would answer a landline telephone differ from the overall distribution that we'd expect significantly? So what we have here is one list, right? 141, 186, 224 in each of these age groups. What we're going to need is an expected list of counts. Okay, and how we would go about getting that is by thinking about this total. The total of people we contacted was 1,048. We'd expect 19.1% of them to be in their 20s, right? That's what it says here, 19.1%. So to find this, I would take 0.191, 19.1% of the 1,048. That will get me my expected count. In the next group, I expect there to be 21.5% of everyone that are in their 30s out of 1,048. So this is how I'm going to get my expected counts in this case. It's not like everything's equal, like when we're rolling a die. If the die is fair, we just divide the total by 6. Here we have a claimed distribution of ages. Folks that are in their 50s are 0.155 out of 1,048. And then those over 60, we had expected that to be 22.8%. Okay, so that there's no mystery as to how I'm going to come up with my expected counts, because I'm going to need those to run the test. But the way I know this is a chi-square goodness of fit test right away is that there's just one list. Okay, so hopefully I don't have any typos on my expected counts, but just giving a cursory look here, this age group is the smallest percentage and it's my smallest count, so looks like it's okay there in terms of those expected counts. What I like to do with chi-squared is run it first, and then I'll work through everything else afterwards. You'll see why. When we do the other chi-squared and we need the expected counts, and they take a little bit more work on our part to find, the calculator you'll find does them all for you. So I'm just going to go right to stat and test. And I'm going to go up to, I'm going to just run this chi-squared. Remember, make sure we pick chi-squared goodness of fit. This is a goodness of fit situation. We haven't seen the other chi-squared test yet. I don't think we still have 5 degrees of freedom, though. We have 1, 2, 3, 4, 5 categories, which means we only have 4 degrees of freedom. Okay, so we're going to go ahead and calculate. And I get a pretty big chi-squared value of 48.17, so I'm just going to jot that down. And then be careful with this p-value. I'll have people tell me, they'll literally write down that the p-value is 8.69. It's 8.69 times 10 to the negative 10th. Okay, hopefully you see that. So we really have a decimal, 9 zeros, and then the 869. So what I usually do in that situation is I just say the p-value is really small, and the way that I do that is I say it's less than 0.0001. Okay, so there's some discrepancies in a couple of places here if they asked us to, try to figure out why it's there's such a big difference. This age group seems like they're not nearly as likely to own the landline as we'd expect them to, right? Which makes sense. They're younger. This group here too, they seem to answer landlines less than we'd expect. The 40 to 49-year-olds seem to be about equal. This group here seems to be answering landlines more than we'd expect. And then same here, 60 plus, not a big surprise. So it seems like the folks who are in the older age groups seem more likely to answer the landlines, and the people in the younger age groups do not, based on their age. So it's kind of a way of thinking about a correlation or an association without an actual like scatter plot or residuals. We have categorical variables. So to do the hypothesis test start to finish, our null hypothesis would just be that the distribution of people who answer landlines is the same as the population distribution of ages. So you can see a little bit different feels sometimes here. I don't have to like state these parameters and list in symbols. I just have a null hypothesis and an alternate hypothesis, right? The distribution of the ages of people who answer landlines is the same as the population age distribution of all U.S. residents. Or the two distributions are not the same. It's supposed to be the U there. Kind of look like a versus. So now we go to our conditions for inference, right? Did we take an SRS? And it does say up at the top here that they were randomly dialing landline telephones, okay? So we have that. And then we don't have a condition for normality. As soon as I see you write normality here, you're going to lose points. You won't get credit for your conditions for inference. Chi-squared distribution is skewed to the right. It's not normal. We have no such assumption of normality here. What we need for chi-squared is for all of these expected counts to be greater than or equal to 5. And we have them listed up above. So we're good on our expected counts. Oh, sorry, greater than or equal to 5. I think I misspoke and started to write the wrong thing. They're all greater than or equal to 5. So we're good on that. It's very similar to the normality where we need like a large sample, or we need n times p, n times 1 minus p, but that's not really what we're looking for there. So, and they're listed above. Normally we would make sure you list them if you're doing a significance test here somewhere. Show that you found those expected counts. Don't just say that they're greater than or equal to 5. And of course, we sampled less than 1/10 of the population. All right. And now we're going to run our chi-squared test, which again, we already did. We're going to get a p-value. That's sort of my fourth part to a hypothesis test. And then the fifth part will be my conclusion. So I'll jump back to my calculator. Chi-squared was really large. Remember, 48.17. And the p-value is less than 0.0001. It's really, really small. So in our statistical language, we would reject the null hypothesis. And if we wanted to go a step further, sort of how I was thinking earlier, and say how they're different, well, then we can look at the expected values and the observed values, or we can actually go to our chi-squared. See these contributors to the chi-squared? We can see how big they are. That first group contributed a value of 17 to chi-squared. The next group contributed 6.7. The middle group contributed the least. There's not a big difference in that one from what we'd expect. And then the last two groups contributed 14.5 and 9.2. So you can see the contributions to that 48.17 come mostly from the younger demographics and the older demographics. That's seems to be where the bigger difference is, if they ask us such a question. But here it just says, is there convincing evidence that the distributions are different? And in this case, there is convincing evidence that these two distributions are different from each other.